Okay, in this lecture, we're going to finish our section 1.2 material on the calculus of parametric curves. So in the first part of that section, we had talked about finding the first or second derivative of a parametric curve, which can give us information about the tangent line or slope of the tangent line to a parametric curve or its concavity. So in this second part of the section, we're going to talk about some problems involving integration of parametric curves. So let's start by thinking about the question of determining the area that lies under the graph of a parametric curve, which may not necessarily be the graph of a function. So how would we find the area under a parametric curve? So here's how we do it. The following theorem gives us a formula. Let us consider some non-self-intersecting plane curve defined by the parametric equations x of t and y of t, where t ranges from a to b. And let us assume that the equation for x is differentiable. Then the area under the curve defined by those parametric equations on that interval from a to b is given by the following integral. So the area is the integral from a to b of the product of y of t with the derivative x prime of t dt. So let's think about why this formula sort of makes sense. So a little scratch work to the side here. Let's suppose that we have some parametric curve, non-self-intersecting. Let's call that curve C. And we're looking at that part of the curve that is defined from t equals a to t equals b. So our initial point here corresponds to t equals a, and our terminal point would correspond to t equals b. So what we're interested in would be, say, the area under that parametric curve on this x interval, where our left-hand x endpoint would be the value of x where t is equal to a, and our right endpoint would be the x-coordinate at the terminal value when t is equal to b. Now and then our height here of this curve is given by y of t. So we know that the area under the graph of a function, so here our function would be the function y, would be the integral of that function y. Let's write it like this. Let's say y with respect to x, where the range of x values goes from x of a to x of b. So we could calculate it like this, or this is actually how we would calculate that desired area. But since we're working with a parametric curve, we have parametric equations describing the x and y coordinates for points on that curve. So we'd like to try to transform this integral from an integral in terms of x to an integral in terms of t. Now to do that, well, let's see what we would need to do. So our limits of integration in terms of x are changed to limits of integration in terms of t. So we're integrating from our initial point, which is corresponding to t equals a, to the terminal point, which is t equals b. And y, the y coordinate for any point on that curve, is a function of t. It's given by y of t. So y is replaced by y of t. And then we're left with, on the end, the differential of x, dx. So recall, if x is equal to some function, x of t, then the derivative, which would be the quotient of these differentials, dx dt, would be just x prime of t. So solving for dx, we would have dx is equal to x prime of t dt. So recall the formula, or the definition of a differential. The differential of x would be the derivative of x times the differential of t. So our dx is replaced by x prime of t dt, and we now are integrating a function of t over some interval of t values, namely from a to b. So this formula sort of makes sense from our formula for the area under the graph of a function. So let's take a look at an example of this. Suppose that we're interested in finding the area enclosed by an ellipse. And we saw that an ellipse can be parameterized by making use of the sine and cosine functions. So we saw that in our section 1.1 material. So here we're looking at the ellipse whose parametric equations are x is given by a sine of t and y is given by b cosine of t, where t is ranging from 0 to 2 pi. So let's see if we could just sketch that ellipse first before we find the area enclosed by an ellipse. So in the xy plane, let's try to sketch this. So how do we know it's an ellipse? Well, from our parametric equations, if I solve for my first equation for sine of t, I would have x over a is equal to sine of t. And solving my second equation for cosine of t, I have y over b is cosine t. So taking the sum of the squares of those values, that is x over a squared plus y over b squared, I would have the sum of sine squared t plus cosine squared t, which is 1. So this is really x squared over a squared plus y squared over b squared is 1. Which we recognize is the equation of an ellipse, where our x-intercepts would be positive and negative a, and our y-intercepts would be positive and negative b. So in this case, well, a and b are arbitrary. I've drawn them where a is a larger number than b. So we would have an ellipse that looks something like this. And here, let's see how we would be traversing this. So our initial point where t equals 0, we would have the point 0b. So we're starting here. And as t starts to increase from 0, we see that x of t would be increasing. So we're traversing the curve in this direction. So as we range from 0 to 2 pi, we make a full revolution about this ellipse, and we end up back at our starting point. So within that interval, the curve is not self-intersecting. It only intersects itself at that same initial and terminal point, but we're not like doubling over the curve. So what we're interested in is the area enclosed by that ellipse, this shaded area here. So we can use our new formula for the area under a parametric curve to find this area. So let's take a look at it. So here, our formula for area is given by the integral from a to b, where a and b are the endpoints of our t interval. In this case, 0 and 2 pi. Then the function that we're integrating is the product of y of t. So here we have b cosine t times the derivative of x. So here x is a sine of t. The derivative is then a cosine of t with respect to t. So taking the product of these two terms, well, we have a constant b times a, which we can bring out in front of the integral as the product ab. And we're integrating from 0 to 2 pi. Well, we're left with a cosine of t times cosine of t, which would be cosine squared t dt. So now we need to think back to some Calculus 2 material on techniques of integration. If we're trying to integrate even powers of sine or cosine, we can make use of a trig identity. In this case, a double angle or half angle identity. So recall that we can rewrite cosine squared of t as 1 plus cosine of 2t all over 2 dt. So here, to make my work a little bit easier, this division by 2 in my integrand, I can think about as multiplication by 1/2, and then pull out that constant factor 1/2 in front of my integral. So I have ab over 2 times the integral from 0 to 2 pi of 1 plus cosine of 2t dt. So let's see what we have for our antiderivative. We have ab over 2 times the antiderivative of 1 with respect to t would be 1t, and then plus the antiderivative of cosine of 2t is 1/2 sine of 2t. That factor of 1/2 out in front is actually coming from a u substitution there. And the fundamental theorem of calculus says once we find that antiderivative, we evaluate it from 0 to 2 pi. So let's see what we have. Out in front, we still have our constant ab over 2. Then we're multiplying by the value that we get by substituting our upper limit of integration, 2 pi, into this antiderivative. So we would have 2 pi plus half of sine of 4 pi. Now sine of 4 pi would be 0. And then we subtract what we get when we substitute 0 in for t. So we would have 0 plus sine of 0, which is 0. So we're left with ab over 2 times 2 pi. Our plus minus, our 2 and division by 2 cancel. And so we are left with ab pi. So this is a formula for the area enclosed by an ellipse. Whatever those constants a and b are, those are the x and y intercepts. The area enclosed by that ellipse is the product of a and b with pi. Or in the general case of a circle, where a and b are the same value, which would be the radius of that circle, we would have pi times the product of a with itself, or the radius squared. We have pi r squared for the area enclosed by a circle of given radius. Okay. Now, in the next part of this section, we'll talk about calculating the arc length, or total length of a parametric curve. So let's suppose that we have some parametric curve C, where our initial point corresponds to A, and our terminal point corresponds to another value, t equals B, and we want the total length of this curve. So maybe we're looking at some object traveling through the plane, and we want the total distance traveled by this object. So the total length of that curve, or the arc length of this curve. So how do we find it? Well, the following theorem gives us a formula for the arc length of a parametric curve. So again, suppose we have a plane curve defined by parametric equations x of t and y of t. where t is varying from a to b. And let's assume that the equations x of t and y of t are differentiable. So the arc length, or the length of this curve, is given by lowercase s, I believe is the notation used in your online textbook. In some other textbooks or homework problems, you might see arc length denoted as capital L instead of S. It's just a matter of personal preference what you want to use. So here it's given by the integral from a to b of the square root of the sum of the squares of the derivatives of these equations for x and y. So that is, you find the derivatives of your parametric equations, dx dt and dy dt. You square them and take the sum of those squares, then take the square root of that sum and integrate it over your t interval. And you will have the arc length of this curve. All right. So let's look at an example making use of this formula. So here we are asked to find the arc length of the curve given by these parametric equations on the interval from 0 to 2. So let's take a look at it. Here we will start by finding our derivatives of these parametric equations. dx dt is equal to 3 minus 3t squared, and the derivative of y, dy dt, is equal to 6t. So once we have these derivatives, we can substitute into our formula for arc length, which is s equals the integral from a to b. In this case, our t interval is from 0 to 2. And we're looking at the square root of the sum of the squares of these derivatives. So our first term was 3 minus 3t squared. We're squaring that. And then we are adding 6t quantity squared and integrating with respect to t. So let's see what we have here. We have the integral from 0 to 2 of the square root of, expanding this first expression squared, we have 9 minus 18t squared plus 9t to the fourth. And then we are adding 6t quantity squared, which is 36t squared dt. So combining some like terms under the radical, we have 9. We then had a negative 18t squared plus 36t squared, which gives us positive 18t squared. Plus a 9t to the fourth dt. Now, this expression under the radical can be factored. So if we first factor out a 9, it helps to see how to factor a little bit more clearly. We have 1 plus 2t squared plus t to the fourth dt. And then that fourth degree polynomial can be factored as 1 plus t squared quantity squared dt. So simplifying a little bit, well, for our integrand, we have the square root of 9, which is 3, times the square root of 1 plus t squared quantity squared, which is 1 plus t squared dt. Or if we prefer, we can leave the 3 distributed as 3 plus 3t squared dt. So finally, after a lot of simplification, we are ready to integrate this expression. So we have, for an antiderivative, 3t plus t cubed, and we then evaluate this integral from 0 to 2. So substituting 2 in for t, we would have 6 plus 2 cubed is 8. And we subtract the value that we get when we substitute 0 in, which is 0. So we are left with 6 plus 8, or 14, for the length of this parametric curve on that interval from 0 to 2. Okay. So let's look at one last concept in this section, the concept of calculating surface area of some surface obtained by revolving a parametric curve about a line. So in this last part of our section, we will define how or give a method for calculating the area of the surface of revolution for a parametric curve. So the idea is the following. If we consider a plane curve, which is a parametric curve defined by the equations x of t and y of t, as t ranges from a to b, then we might be interested in finding the area of a surface generated by revolving that curve about the coordinate axes, say the x-axis or the y-axis. So in order to find the area of the surface we would obtain by revolving about the x-axis, we would have the following integral for surface area. So we would denote it as capital S, or I've seen some texts use SA for surface area. So again, just a matter of notational preference, what you prefer to use. And it's found by taking 2 pi times the integral from a to b of y of t times the square root of the sum of the squares of the derivatives of x and y integrated with respect to t. Or for revolving our curve about the y-axis, we have a similar formula. Our surface area would be 2 pi times the integral from a to b of x of t times the square root of the sum of the squares of those derivatives integrated with respect to t. So the only difference there is that if we're revolving about the x-axis, we have a y of t, and if we're revolving about the y-axis, we have an x of t. So let's take a look at some examples making use of these new formulas for a surface area of revolution. Or maybe before we jump into some examples, let's kind of illustrate what we're talking about here. So we have something like the following. So let's suppose that we have in the xy plane some parametric curve, C, and we're looking at the part of that curve between 2 endpoints, say an initial point and a terminal point corresponding to t equals a and t equals b. And let's say that we take that curve and we revolve it about the x-axis. So we would be tracing out a surface. Let me see if I can give a rough sketch as to what we would have. So here, not drawn very nicely, but if we were to revolve this expression or this curve about the x-axis, we see that we would have a strange shaped sort of solid whose edge is defined by this curve, and we want the surface area of that solid. So in order to find this, we can kind of think about it like a cylinder. So you had some similar formulas from calculus 2, say the arc length of a function. If you revolve about the x-axis was given by 2 pi times the radius of your cylinder, which is varying here. So at different points, the height of this sort of cylindrical shaped object is given by y of t. And then we're multiplying by the differential of arc length. So we have, in general, for the surface area of a circular cylinder, we would have 2 pi times its radius. Now here, the radius of our cylinder is varying. It's given by y of t. And then we multiply by the height of our cylinder. So the idea is the height of our cylinder can be thought of as this arc length differential, which is where the square root of the sum of the squares expressions come from. Now, of course, we could have a similar problem where we're taking that curve and revolving it about the y-axis instead of the x-axis. We would have a different shaped solid, and the surface area of that solid is then given by this second formula, where the radius of our cylinder is defined as x of t instead of y of t, and we're still multiplying by the differential of the arc length for that curve. So a little bit of an intuitive idea as to where this formula or these formulas are coming from. So let's consider some examples here. So in our first example, we're asked to find the area of the surface obtained by revolving the curve, whose parametric equations are given here, where t ranges from 0 to 1, about the x-axis. Okay. So let's set up our integral for surface area. So we have a constant 2 pi times the integral with respect to t, where t was ranging from 0 to 1. And since we're revolving about the x-axis, we're taking y of t, which is 3t squared, times the differential of arc length, which is the square root of the sum of the squares of the derivatives of x and y. So for the derivative of x, we have 3 minus 3t squared. We're taking that quantity squared and then adding the derivative of y, which is 6t, and we have that quantity squared, dt. Okay. So we have a constant 2 pi times the integral from 0 to 1 of 3t squared. And now notice, to save ourselves a little work, this expression under the radical is exactly the same expression that we had from this previous example. So in order to save ourselves some work, well, rather than expand and collect like terms and factor again, we saw that this expression under, or the square root of the sum of the squares, reduced to 3 plus 3t squared. So using the work that we had done in our previous example, this second term reduces to 3 plus 3t squared dt. So in this step, maybe just put a note to yourself in your lecture notes. See the previous example to see how that simplification occurs. So now, simplifying just a bit further, we have a 2 pi times the integral from 0 to 1 of 3t squared, which we're then distributing. So we would have 9t squared plus 9t to the fourth dt. So now we have a constant 2 pi times the integral, well, let's see, we're ready to find our antiderivative at this step. So times The antiderivative of 9t squared would be 3t cubed, plus the antiderivative of 9t to the fourth would be 9/5 t to the fifth, evaluating from 0 to 1. So we have a 2 pi times, when we evaluate at t equals 1, we get a 3 plus 9/5. We subtract what we get when we evaluate at t equals 0, which is 0. So let's see what we're left with. We have 2 pi times 3 would be 15/5 plus 9. So that's going to give us 24/5 times our 2 pi gives us 48 pi over 5 for that surface area of the solid obtained by rotating this curve about that x-axis. Okay. So let's look at one last example to finish out this section. Here we are asked for the area of the surface obtained by revolving the curve given by these parametric equations about the y-axis. So again, let's set up our integral for the surface area using our previous theorem. The surface area is given by 2 pi times the integral from 0 to 1 of, since we're revolving about the y-axis now, we would have x of t, which is e to the t minus t, times the square root of the sum of the squares of the derivatives of these parametric equations. So we start by looking at x prime, which is e to the t minus 1. We're squaring that quantity. And then we add the derivative of y, which would be 2e to the t over 2 power, quantity squared, dt. All right. So let's simplify this. We have 2 pi times the integral from 0 to 1 of e to the t minus t times the square root of, so expanding our first term squared, we would have e to the 2t minus 2e to the t plus 1. Plus, when we square this second term, we have 4e to the t dt. So we're left with 2 pi times the integral from 0 to 1 of e to the t minus t times the square root of e to the 2t. Then we had a minus 2e to the t plus 4e to the t, which leaves us with a positive 2e to the t plus 1 dt. And now this expression under the radical can be factored. Let's see how it factors. So we have a 2 pi integral from 0 to 1 e to the t minus t times the square root of this expression under the square root factors as e to the t plus 1 quantity squared dt. So when I'm taking the square root of that quantity squared, I'm then left with e to the t minus t times e to the t plus 1 dt. So we're getting a little closer to being able to integrate this or find an antiderivative. And in my last step for simplifying, I need to expand this product. So for the product of my first two terms, e to the t times e to the t, I have e to the 2t, plus for the product of the outside two terms, I have 1 e to the t. For the product of my inner two terms, I have negative t e to the t, And then for the product of my last two terms, I have a negative t dt. All right. So finally, we're ready to try to find an antiderivative. So let's take a look at this. We have 2 pi times, well, the antiderivative of our first term, e to the 2t, is 1/2 e to the 2t, plus the antiderivative of e to the t is e to the t, minus, now this third term is what's a little tricky. We have t times e to the t power. So we've got a product of two functions that we're trying to find the antiderivative of, which means that we're going to have to use the technique of integration by parts from Calculus 2. So for now, let me do a little scratch work. Let's say at the top, I need to find the antiderivative of t times e to the t, dt. So using integration by parts, I'm going to choose u as t, in which case dv is everything else, e to the t dt. And then I need to calculate du, which would be 1 dt, and v, which would be e to the t. So using our integration by parts formula, I have the product, or this antiderivative would be given by the product of u times v, so that is t e to the t, minus the integral of v du. So v was e to the t, du was dt. So I'm left with t e to the t minus the antiderivative of e to the t, which is e to the t. In general, we would write a plus c on the end, but since we're evaluating a definite integral in this problem, we don't need the plus c. So this third piece, we are subtracting that quantity. So we'll have a minus t e to the t, minus the negative gives us plus e to the t. And finally, this last term, we have a minus t, so the antiderivative would be minus a 1/2 t squared. And we're evaluating this expression from 0 to 1. So let's see what we're left with. We have a 2 pi times 1/2 e squared plus e to the first minus 1 e to the first plus e to the first minus 1/2. And then we have to subtract what we get when we substitute in 0. So let's see. So we are subtracting when we substitute 0 in for t. Let's see what we're left with. So we have 1/2 of e to the 0, which would be 1/2, plus e to the 0, which is 1, minus 0, plus e to the 0, which is 1, and then minus 0. All right. So a little more simplification. We have 2 pi times a 1/2 e squared. We see that our plus e minus e will cancel, and we're left with just a plus 1e. And then grouping our constants, we had a minus 1/2 minus another 1/2 would be negative 1, and then we're subtracting 2 more from that, so we're left with a negative 3. So the following expression, finally, would be the surface area for that solid of revolution. So we see in this case, took quite a bit of work to simplify our integrand, and even after we did, we still had to make use of integration by parts to find the antiderivative for part of our function. All right.